All right, here we go. And we're in 2.2, separable equations. All right, there's where we are in the book. And let me scroll down to the right page here. Whoa, that goes fast. Way too fast, okay. Page 66, we need to do on 51. I'll get there in a minute. Sorry. I would have had all this set up today, but my wife needed to get a prescription from me so she could put it at Walmart, and then they required me to give her permission, and it was just a mess. So anyway, that took time. I wasn't planning. Okay, here we come up on page 50. Actually, we need page 50. All right. Somewhere right in here is where we are. I think we passed it. Okay. Let me go on up a little bit higher to get the whole picture. All right, here's example 4. That's where we left off. Now, y'all probably can't see that yet. Let me get back to Zoom. All right. Oh, and Dawson's waiting. Sorry, Dawson. He can't hear me, so that's why I'll apologize now. So all we're missing is Corbin this morning. No one can rouse Corbin up, can they? Okay. Sorry we're a little late getting started, but there were some technical glitches. Screencast-O-Matic wasn't cooperating this morning, but now we are recording, so I think we're okay. First off, any questions, concerns, problems, issues?
I had a question about problem 9 on the test.
Okay, hold on just a minute. Let me get it in front of me. I don't have it memorized yet, but okay, here we go. Problem 9. Okay. That's y is equal to c1 e to the 3x plus c2 e to the minus x minus 2x. That one? Is that how it starts?
That's what I'm trying.
Say again?
I'm trying to figure out how to start it.
Okay, okay. Now what I just read to you was a 2-parameter family of a second differential equation, and then they give you the differential equation. Now it says, find a solution of the second order initial value problem, that's IVP, consisting of the differential equation, and all you do is add this initial condition to it. Actually, 2 initial conditions. What y is at 0 and what y prime is at 0. Now, would it be helpful for me to go in there and find the test so you can look at what I'm saying? Would that be helpful? You got it in front of
me.
Okay. So what you do is get ready to kick yourself, but don't sprain an ankle or something. Okay. All you do is on that.
You just take the derivative and then plug it in.
No, okay,
Yes.
Yeah, you will need to take a derivative at some point. Okay, but first, okay, you plug in y is equal to 0 to the equation that you have there, right? The solution. That will probably, I'm trying to think if that will eliminate one initial constant. I don't think it will. It might, but I don't think it will. So yes, you do have to take the derivative of that y that you see there, that is your solution, and that gives you 2 equations. You plug in 0 for the x in both of those. Now you have 2 equations, 2 unknowns, and you solve it by elimination what? by addition is what they used to call it in algebra class. If you want to do a matrix, you could do that, but it's so much easier to just do elimination by addition. Does that make sense?
Yes, it does.
Okay.
I think just because I didn't know what IVP meant, it kind of,
Yeah.
I hadn't seen that abbreviation, it just kind of messed with me.
Right. Okay. Yeah. Initial value problem, which, as I said, also stands for InterVarsity Press, but that's a different issue. Okay. Now, yeah, does that answer what you needed?
Yes.
Okay. Any others? Good question.
I submitted mine last night. I didn't know if you received it.
When did you submit it?
I submitted it yesterday around like 6, I think,
Okay.
on Blackboard. I didn't know how we were supposed to submit tests, whether it was through formal email or whether through Blackboard.
Yeah. Either way would work. I was still teaching at 6 because my class went till 6:30 last evening. Let me think. Yeah. No, I'm sorry, till 6:15. Went till 6:15. Tonight it goes till 6:30. I'm getting my days crossed up. So I was still teaching around 6, and frankly, when I finished teaching, I had to shut everything down, and I then did the Zoom invites for today, and I had a couple other things to do, and I was planning to come back up and check emails and messages, and I just ran out of steam, so I didn't make it back up to do that yesterday. So it's probably still sitting there. I can go look if you want me to, but the odds are if you send it that way, it's there.
No, that's fine.
Okay, I do have some time. I have this class and then another class at 11, and that finishes at 1:15. Then I usually eat lunch from 1:15 to 2:15 approximately. I don't usually take an hour, but sometime in that hour I usually eat my lunch. And then so I'll be back up here in the office from 2:15, maybe earlier, until 3. I'll be here after 3, but I've got 2 appointments from 3 to 3:30 and 3:30 to 4 with advising, and then I'll be available again from 4 until 5, and that's when my next class starts. So I have an hour or 45 minutes between lunch and my advising session, and then an hour. If I can get them done in those times, I will do that. And once I print them, I'll send you a message back saying that I printed them, and I'll grade them when I can get to it.
Okay, thank you.
Okay, now here's another thing, and it's sort of good that I planted Billy there so she could ask that question. No, the odds are, the odds are, probably not going to get a lot of stuff done this weekend. And the reason is we're going to have to make a trip to Georgia this weekend. We are not really all that keen on it because of the situation with COVID and stuff, but we're planning to leave very, very, very early in the morning and only stop for gas when we need to, which is probably just going to be one time. And the reason we leave early, my wife, the infectious disease epidemiologist, figures that the earlier we get away and we have to make a stop, fewer people will have been in the establishment before we had to stop. If we wait till late in the day, yeah, it's going to be. So we're leaving incredibly early in the morning. Then we'll get to the farm. We're going to be basically isolated there except for my family members. And they've already been told we're only going to meet outside or on the porch, outside porch, you know. But we're going to be working the whole time too. So it's going to be a working weekend. And because of that, we don't want to come back Sunday evening because of then you run into all the more people and stuff. So we're leaving very, very, very early Monday morning and try to be back before my 11:30 class on Monday morning. So the odds are there's not going to be a lot of grading done this weekend. So I'll get done what I can today, but after that, I'm going to take it with me. But the odds are at the end of the day, I'm going to be so beat, I'm probably not going to have much energy to grade. But if I can, I will. So it may, and then Monday morning is usually a big set of office hours for me. We're going to be on the road. I'm not going to get graded then, so I'll be catching up all next week. So sorry about that, but I'll let you know It's going to be a busy weekend. First weekend like this, we've gone out of town in such a major way. So anyway, don't expect to see Blackboard filling up anytime soon. Okay. All right. Any other questions, issues, concerns? All right. If not, let me go to the screen share here and pull in Billy's PDF. Okay, thank you, Billy. Seems to be working well, wouldn't you say? Can you see that?
Yes, sir.
All
Yes,
right,
sir.
good deal. Do you think this is better than what we were doing?
Yes.
All right, good deal. You can't see it, but I have a bunch of names over here on the side that I'm going to move to the top, I think, because that's not in the field of view for my book here. All right, we did example 4 last time, initial value problem. IVP, there it is. Okay, they didn't say IVP, but maybe it was just the typist was abbreviating because he didn't like the type. That may be the issue in that test. Okay, solve this equation. We've already done this. It's just a review. E to the 2y minus y cosine x dy dx is equal to e to the y sine 2x. Initial value y of 0 equals 0. Now the reason you can get away with just one here, it's only a first order differential equation. The one Melissa was asking about was a second order differential equation, meaning you have 2 initial conditions, but they must be at the same place. Now they don't have to be at 0. Whatever the first one's at, the second one must be at the same value. That one she was asking about, number 9 on the test, they were both at 0, which is fine. They have to be at the same place. But with a second order differential equation, you've got to have 2 initial conditions. One, what y is at some value, the other, what y prime is at the same value. Now, as you saw in that problem she was asking about, these values over here would be different, okay? And that's fine. You use those when you take your derivative and do the things you're doing. Okay, so anyway, we're not having to worry with that now yet. What we're doing, this is all a function of y. This is all a function of x. This, of course, is a dy. Get your dx over here on this side. Write it in differential form. This is a function of y alone. This is a function of x alone. All these functions are multiplied together. So get all the y's with the dy here, meaning divide both sides by y e to the y. Get all the x's with the dx, which you moved over here, and that means you're dividing by cosine x. Okay? So your left-hand side becomes e to the 2y minus y divided by e to the y. That's what you got here, dy. And the right-hand side becomes sine 2x divided by cosine x times dx. And that's over here. I shouldn't say times, well, it is times dx. Okay. Now, before integrating, let's do what makes sense, what they call termwise division. In other words, e to the 2y divided by e to the y is just e to the y. And y divided by e to the y would be y times e to the minus y. I never like to divide or integrate variables in denominators. If I can get away with it, I like to write them in exponential notation. So that's what they've done here. And over here, without doing, oh yeah, here they told you, sine of 2x is 2 times sine x cosine x. Therefore, the cosine x will cancel out the cosine x here, and you just have 2 times the integral of sine x. Okay, we've already done this. This gave you e to the y. That integration was pretty easy. This one was an integration by parts, and I think we did that in gory detail, and that gave us y e to the minus y plus e to the minus y, and then plus minus 2 cosine, because the antiderivative of sine is negative cosine. And then we had our constant of integration. You don't need to do one on this side and one on this side. Just do one, okay, plus c. Now, the initial condition this is our solution in parametric solution. So we use our initial condition to eliminate the parameter. So we'll plug in x equals 0 and set y equal to 0. Well, e to the 0 will be 1 plus 0, that's going to be 0, plus e to the minus 0, which is 1 over e to the 0, which is 1 over 1. So this side gives you a 2. This side gives you 2 times, and the cosine of 0 is 1. So you have a minus 1 plus c. Minus 2 plus c. So 1 plus 1 is equal to 2, minus 2 plus c. Add 2 to both sides. You get 2 plus 2 is 4. High-level math is equal to c. That's your constant of integration. So your solution is y. And I'm sorry, this is where we picked up to yet last time. We got this far last time. I just talked you through what we're doing here. You put the initial condition, y is equal to 0 when x is equal to 0. Okay, that's what this tells you. You plug that in here, and I just did it without realizing I did. That's where we picked up this time. 2 plus 0 plus 2, that's 4, is equal to minus 2 plus, 1 plus 0 plus 1 is 2, minus 2 plus is equal to minus 2 plus c. Add 2 to both sides. C is 4 then. So they're right down the left-hand side just like it was. Y plus y e to the minus y plus e to the minus y is equal to, and they put this 4 in front, which I like to do too because I don't like leading off with a minus sign, 4 minus 2 cosine x. And that's your solution. Okay. Now, any questions on that? All we had to do left over was figure out what the initial value was, or how that solved your parameter. Okay. Now, this next blurb here is on use of computers. Now, this is a computer graphic. I'm not about to draw this thing of these solutions to this differential equation here at various values for c. Okay, and I don't even see where they put any of these in here. These are just a family of curves. This is c equal 4 here, which is the one we had. There's a c equal 2 down here, so the one in between that, this one right here was c equal 1, so this must be, no, 3 here. Whoop, 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 whoop. Here's Corbin. Good deal. Perfect attendance today. Love to see it. Way to go, team. Okay. Welcome, Corbin, when you get here. Okay. Now, as soon as Corbin came in while we were talking, this thing, you can see this block in the middle of the bottom of the page. Do you see that? A rectangle?
Yes, sir.
Does it block out the wording?
It does.
Yeah, but then it fades out and you see it again. Corbin's to blame for that, I have you to know, okay? Because when he comes in, for some reason, Zoom wants to cover his name, so no one else can see that. And now, from now on, this will be coming in and out. I've tried everything I can think of to do. Someone told me, don't expand the screen. Well, I didn't expand the screen. It still happens. But I moved this taskbar to the bottom, so hopefully it's going to minimize. So I'm guessing right now that what they did in this graphic, this was c equal 4 here, 3 there, 2 here, probably 1 there, 0 I'm guessing there, and then you go on down to negative numbers. And this, if that was 4, this is probably 5, 6, 7, 8, 9, and 10. So I'm just guessing that's what they did to draw this. They showed you 2 of these. Our initial condition, if you recall, got to scoot back up just a little bit. A lot. Initial condition, when x equals 0, y is equal to 0, the only one of those curves that passes through the origin is this one, and that was the one when c is equal to 4. Okay? And that verifies that we did it right here. C is equal to 4 is that solution. All right. I guess they're just showing you the connection between the analytical solution and the graphical solution. Any questions on that? Okay. Now, they do a lot of blah, blah, blahs here. And I don't know if the rest of it is worth saying anything about. So what I think I'll do is go on to the next page. And they're talking about here numerical solvers. That's, I guess, what they're talking about here. And in section 2.6, we'll discuss a little bit about using numerical solvers. We'll do some solutions in a very crude numerical solver, not one that they really use. Okay. So let's see, anything else here? So that initial condition led to a particular solution, and if it does, it yields a specific value of C in the family of solutions on first order differential equations. There's a natural inclination for most students and instructors to relax, be content. Don't do that. The solution of an initial value problem might not be unique. And we went over that before. We saw an example 4 of section 1.2 way back there. The initial value here actually has two solutions. Of course, when y is equal to 0, derivative of y with respect to x would be 0. That would be a solution. But we also saw that y is equal to 1/16 x to the 4th. And that also, when x equals 0, y is equal to 0. So both of those work, okay? But they're two different solutions. One solution is now this is maybe a slightly different problem here, but it would have been that quartic solution that does like this. The other is the line y is equal to 0. And they sort of show something similar to that here. Now, if you recall, there was a condition that we looked at to see if we can predict whether there's going to be more than one solution. And I believe it was that the function and its first derivative must be continuous over the interval that you're talking about. And when you do a first derivative of this one, you wind up with a y to the -1/2 ultimately. You cannot put a 0 in there. And that's why the place at 0 did give you two solutions. Okay? Both of them valid solutions, but that's eliminated your possibility of saying, that's your unique solution, because it didn't fit. But we're through with that. Let's move on down. And I've got to move because that block's in the way. No. So we're in a position now to solve the equation. This equation right here. They showed you how to solve it before. Now we're going to solve it. You separate the variables. Now, would you rather I talk through this or do it on the whiteboard? Doing it on the whiteboard shows you the steps. And the other is a lot of blah, 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 which you can not interact with or not. What you prefer?
Would be easier to see.
Say it again.
I think a whiteboard may be easier to understand it.
I think so too. The only reason I talked through that previous one, we had already done all that work except for plugging in. All right, so that's what we're going to do now, is take this equation here with that initial condition and see if we can solve it. So let's go to the whiteboard. And you get to watch my fingers do the walking. Now, this block of names is in the way again, so I'm going to move you again. And I'll move you as far, not that it matters any, but as far north as I can. You can't see that. And then there's also a toolbar up here that's in the way, so I'm going to move it as well. Okay. Now, I'll use as much whiteboard as I can. This function now it was so obvious on the other. Oh, here it is, top of the page. dy dx is equal to x y to the 1/2. Okay, that's the differential part. dy dx is equal to x y to the 1/2 that's the differential equation. The initial condition is y at 0 is equal to 0. Okay. Now, how would you proceed to solve this? Last time they gave us a solution, then they gave us another solution, verified, that kind of stuff. Now we're actually solving it. How would you suggest we go about doing that? What's the only technique we've learned so far? Separation of variables. Okay, so what we want to do is get all the y's over here with the dy, move the dx, write it as a differential form. So get the dx over here in differential form and leave the, oh goodness, I didn't do that. I didn't mean to do that. This whiteboard sort of has a mind of its own. Okay. Okay. So first thing we're going to do is write it in differential form, and that would be dy. And by the way, the form that you see it here is what they call normal form, differential on this side and everything else on this side. Now we're writing in differential form, which is dy is equal to x, y to the 1/2 times dx. Now, okay, it's in differential form, but the variables are not separated. You got the x's together, but the y is mixed up over here with the x's and not over here with the y. So what we do, since it's separable, meaning that it's a product, you can divide both sides of the equation by y to the 1/2. Okay, and that's a pretty ugly y. Okay. Okay, and right there, if you pause to look at it, that's where our problem arises. Okay, the y to the 1/2 cancel out on this side, and what we have now, I'm going to rewrite this ever so slightly to be y to the -1/2, because I don't like trying to integrate with a variable in the denominator, dy, unless of course it's just y and x down there or y down there, and then that would be a log x, okay, or log y, whatever. So there's this side is equal to what's left over here is just x dx. Yeah, ugly x. Okay. Now what we do is integrate both sides. Now, what I was starting to say before, I got it out but didn't finish it. Here's where you see your problem comes. You see, this right here tells you y cannot equal 0. And yet we have y equals 0 as your initial condition. That's why we have a problem here. That's why we have a singular solution because you've just done something that you can't do. You can't have y equals 0 and divide by y to the 1/2. Square root of 0 is 0. So that's where your problem came in, okay? And it wasn't completely obvious here, but as soon as you separate the variables, it becomes very obvious that you can't do that, okay? So you can still solve it, but you're not going to have a unique solution. You'll have two solutions, okay? So how do we do this integration? What would that give us? Somebody? Uh-oh, Cal 2 teacher, need to get in touch with you. It's a power rule. Increase the power by 1. In this case, that would be 2/2. Minus 1/2 plus 2/2 would be 1/2.
1/2.
And
That'd
then,
be
say
is
again?
it 2y 1/2.
Yes.
Divided by
Then
1/2.
you divide by 1/2, which is the same as multiplying by 2 over 1. So there's the left-hand side. Remember, you don't need to mess with the plus c there. 1 plus c will do, and we'll do it on the right. Right-hand side.
X squared over 2.
Absolutely, x squared over 2. Better be speaking up. I know who your Cal 2 teacher was. Okay? That would have been me. Okay? And here's where we put in our plus c. Even though this probably isn't a well-posed problem, because this can't happen and that can happen at the same time. Okay? Everywhere else, that would have been fine. If you'd chosen any other initial condition, no sweat at all, you have a unique solution. That one, though, you do not. Okay? So, let's clean this up a little bit. And I guess they want to give it as a function of y, y as a function of x alone. So let's do that. Let's divide both sides by 2. So that'll put an extra 2 in this denominator. Okay. Now, when we divide this by 2, it's still a constant. So let's just call it another constant, okay? Because it really doesn't matter. So now we wind up with the square root of y, or y to the 1/2, is equal to 1/4. Goodness gracious, this is ugly. X squared plus some constant. Let's just leave it as some constant for now. Okay? We can write it. I'm still going to call it C, even though it's not the same C as above. If I had been foresightful, I would have called that a C1 up there. I'm not foresightful, so let's just call it some constant, C. Okay. Now, square both sides. And what you have is y is equal to now let's see. Now, for some reason, yeah, that's all they did. They just put it in parentheses and said 1/4 x squared plus c squared. Okay. Now we plug in this somewhat invalid initial condition. Okay. Plug in a 0 for x and put a 0 for y at the same time. So that would be 0, that's your y, is equal to c squared, basically. Okay, so let's just call that a constant. Now that's way a lot too simple. Yeah, well, that just gives you the constant is 0. Okay, so 0 is equal to C. Done. So that then gave your solution as y is equal to 1/4. Well, let's go and square it. Okay, if C is 0 down here, this would be 1/16. So let me this is 1/4 squared is 1/16, x to the 4th. And on the surface, that looks perfectly fine, meets the initial condition, x equals 0, y is equal to 0. Perfectly fine. However, there is another solution out there, y is equal to 0. That's also a solution. And the reason there's two is that this initial condition did not meet, this violated that. Okay, so they did come up with two solutions. Now, it is a solution of the initial value problem, but the trivial solution was lost because as soon as you divided by this, you lost that trivial solution, y is equal to 0. Okay. So, what they're suggesting to you is you can come up with all sorts of other solutions too. Let's go back to the book because I don't want to draw these things. So let's go change my screen sharing back to the text. Okay. Now, the first one would have been that quartic solution. Now, this one actually looks more like a parabola. In fact, it looks way too much like a parabola. The y is equal to 0 would have been this here. So you had either one solution would be the line y is equal to 0. The other solution would have been your quartic solution, which came down like this and went up like this. Now, don't worry about the a's yet. We're going to get to what they're talking about there. Okay? Now, because both of those are solutions, you can mix and match. I think we did this before. You could use that the y is equal to 0 as a solution for any x less than 0, and then this one here, that's still a continuous function. Fine. You could have chosen this leg of the quartic solution to be for x less than 0, and then 0 to be for anything x greater than or equal to 0. Still a unique solution, still a continuous solution, or either one of them. So you have at least 4 different solutions there, depending on how you break those things up. Okay? So that's what they're dealing with here, and you can't see it, but I've got to move you guys to the top again so I can read the text here. So each of the functions all right. With this initial condition, that was our solution. Or y is equal to 0 is also a solution. Now, we're in a position to solve. You got a question, Billy? Or oh, okay. Your light came on. Okay. We're now in a position to solve the equation we thought we had, separating variables and integrating. Oh, we just did this. Okay. I'm sorry, we done that. Now, each of the functions that we talked about here, that one and that one, are both legitimate functions, so you could have done something else and still made it work. Okay? The initial value that we chose up here, y is equal to 0, y of 0 is equal to 0, possesses many more solutions since the choice of the parameter a. Okay? Now, you might say, where in the world did they get this A? Okay. Well, they kind of just made it up, but not necessarily. You could have then changed it to this. Now, this is woulda, coulda, shoulda, without really much documentation of why they're doing this. But if you didn't call the CC, well, actually factored out the 1/4 or 1/16 from it, and then had this as x minus a squared, where basically your C is related to a squared. Not exactly, but somewhat. There's a factor of 16 in there. This then satisfies both. Again, this is taking the 0 here, and then rather than just having when a is equal to 0, in other words, that C is equal to 0, your family of solutions, if you had other values for C, that A could have been moved over here or over here, because all you're doing is translating your x squared, basically. And that's what this is showing. You have a whole bunch of solutions when you combine these together. You could have done the other one, like I said, of using the left-hand side of the quartic solution, and then with using various A's, you could have moved that to the left or right. Okay, this one could have gone this way as well. A could have been over here, and then from there on. So there's a whole series of things you could have done, and the reason is this was not a well-posed problem. You wiped out one of your possibilities, and therefore you don't have a unique solution. Okay, I think we beat that into the ground. Let's move on. Now, you have other possibilities, okay? And I think they said at the end of section 1.1 there was a remark about this. I usually tend to avoid the remarks unless they have something I know we're going to be using. You can have a perfectly simple initial value problem. dy dx is just some function of g of x, and with an initial value when x equals x0, y is equal to y0, define some interval I, but you get down to this stage here and you cannot solve this integral. This is an integral that g of x is not integrable. Okay, I don't know if you remember any of those from Cal 2, but they were there. Okay, and we call that a non-elementary solution. That is one that cannot be expressed in terms of elementary functions. The elementary functions are those that can be integrated, okay, or the result of an integration. For instance, here's one, a classic one. Solve this one. Looks like a simple enough problem, doesn't it? Okay, I'm going to move this up a little bit so that rectangle doesn't get in the way. Let's go on and go to the whiteboard. Okay. All right, to clear the previous one.
Yep.
Okay, we did. All right, now I got to move you guys out of the way here. Okay. Now, here's our problem. dy dx, simple first order differential equation, dy dx okay, is equal to, all right, it looks like a pretty simple function of x alone, e to the minus x squared. Okay, e to the minus x squared. And you're given an initial condition of y at 3 is equal to 5. Okay, there's your initial condition. And this looks like that'd be pretty simple to do, separation of variables. That part is simple. You just write it in differential form. On the left-hand side, you got dy and only dy. On the right-hand side, you have e to the x, e to the minus x squared, that's a pretty ugly 2, dx. Just writing it in differential form, and that's a pretty ugly d. Okay, once you get it in that form, there is no y dependence, there's nothing to move over here, so you integrate both sides. Okay, now, I'll volunteer to do the left-hand side. Integral of dy is just simply y. Sure, there's a plus c, but we'll put that the other side, okay? But you tell me what the integral of e to the minus x squared is. Integration by parts doesn't work, substitution doesn't work, partial fraction doesn't work, ain't nothing gonna work, okay? That is not one that we can do. If there had been an x in front of here, yes, no problem. Integration by parts would have worked fine. There is no x there, okay? So this is a non-elementary integral. There is no you can't do the integration. You leave it in this form, okay? Now, what they're going to do at this stage is make up a dummy variable over here, okay? All right, and that dummy variable will be our t. And we'll call this e to the minus t squared. And in some senses, this seems like a really silly thing to do. Why change it? And this may not be a satisfactory or satisfying answer to this, but it is one. This y is a function of x. This integral that you can't integrate, you need to get it expressed in terms of x, okay? Well, what we're going to do here is put some limits of integration on this thing, okay? We know that y, well, we're integrating with respect to t now, okay? And they're doing something here that I don't find completely, I want to say almost justifiable, okay? And here's what I'm talking about. When this is saying when x equals 3, y is equal to 5. That's what it's saying, okay? Now, this is an integral dy. And they rewrite this, and this is the part that I found a little problematic. So I'm going to erase this line that I did here when I was just showing you can't go any further except putting a plus c by it. Okay, here's how they try to justify what they're going to do next. Okay, rather than writing like this, it's going to put that t in there, but you're going to do it on both sides, okay? Now, this is the part I find a little problematic. They rewrite this as dy, if I could write dt dt. Now, I don't have any big argument there that this here, if you did it, results in that. Okay, I'm fine with that. Okay, what I do have a little bit of an argument with is why they put the limits, what they do. They put the 3 down here and the x up here. And that to me is not completely satisfying. Why? Because t, how do you know t is going from 3 to x? Well, Well, that's sort of replacing your x variable here. And I guess it's okay. It just isn't completely clear that they do it. Over here, it makes more sense, okay? But I guess it's the t's here. You got to do the t here too. So this integral is going to be from 3 to x. Now, this goes back to your second fundamental theorem of calculus, or fundamental theorem of calculus part 2, however your textbook called it. And this was going to be your e to the minus t squared. Remember, we changed this to t squared dt. And this indeed makes sense here, that t, the dummy variable, is going from 3 to x. So you had to put the t in here, 3 to x. But there's no indication what dy dx is here, okay? But here you have an integral of a derivative, and from the other, or is this the same one, fundamental theorem of calculus, this indeed is your y. So this is y as a function of t now. T is just a dummy variable for x, you might say. So that's why it's okay to do this. Y of x, the antiderivative of the derivative of y is, whoops. I get to talking and I neglect what I'm doing. Oh, I erased them both. Didn't mean to. Okay. Y of x minus y of 3 is equal to, and then it's the integral here of 3 going from 3 to x, if I could write, e to the minus t squared dt. Now, what does this tell you? Y of x, that's what you're looking for. That's your solution. Y is a function of x. Minus this. Well, what is that? That's your initial condition. That's why we chose to go from 3, okay? May not have been obvious, but that's what we did. Minus 5 is equal to this thing, this integral we cannot do, from 3 to x e to the minus t squared dt, the non-elementary integral. Oh, that's ugly. Okay. And what they did, they then added 5 to both sides. So you had, well, let's just go back to the book. They left it as y of 3, and I don't know why. But on the next page, so let's go back. Remember that. And go back to the book share. All right. And I got to move you guys around again. Y'all are just always in the way. You know that? Okay. And let's go to the top of the next page. We got this far, except I went on and told you what y of 3 was. It's 5. Okay. So then finally they get around to doing that. And there's your solution. Scoot it on up a little bit further. Okay. Y of x is equal to 5. That's y of 3 plus this thing here. Now, are y'all at all familiar with this function here, this integral e to the minus t squared dt? I think you probably are. That's a close relative of most college students' favorite function in the world. And that function is the bell curve. This isn't exactly a bell curve, but it's a close relative of it. this gives you that shape. And of course, all college students love grading on the curve, don't you? Okay. You scoot your grades around so not everybody's failing, even though it looked like it on their scores. That's what this function is. It's a close relative of the bell curve. Okay. And this does mark the end of the section, and I don't think there's anything particularly attractive here to say here. So let's just skip over that. Okay. Homework exercises. I think I've given most of these before, but let's do them again. Do any of the odds 1 through 21, okay, that you find in the back of the book. Any of the odds 23, either 23 or 25, no, 23 through 27, that you can find in the back of the book. Do 29, it's in the back, if it's in the back of the book. Then do either 31 or 33 if it's in the back of the book. Then I would say do either 35 or 37 if they're in the back of the book. And then do any of the odds 39 to, or do either 39 or 41 if that's in the back of the book. They should be. And then 43 and or 45, I think, or maybe just 43. Let me see. Yeah, do 43 if it's in the back. You don't have to do all these. You choose. Then any of the odds 45 to 49 if they're in the back. And then stop there. If any of the discussion problems are in the back, go on and take a look at them. But most of the time they're not, so I wouldn't worry with them too much. But I always take a look at them to see if there's anything that might be of particular interest. Okay. Any of you civil engineers? Well, if not, I was just going to say the suspension bridge would be right down your alley if you wanted to take a look at that. But it looks like a pretty hairy kind of exercise, but you can go for it. You won't find the answer in the back, but if it's something you want to take a look at. Now, on the right-hand side, there was this thing about computer solutions, computer lab assignments. I don't have a computer lab to make an assignments on. If you do have access to yours at your home campus and you want to play around with some of these, CAS or something like that, want to play around with one of these and see if you can get some fancy looking curves like this and try to figure out what in the world those things are doing, you're certainly welcome to do that. It's not part of your assignment here, though. All right. Enough said. Any questions on 2.2? Okay, how are we doing on time? All right, we go till 10:45, right? Yeah, so we got a little over an hour to go. So let's move on to linear equations. Hey, we thought we'd been doing linear equations. Well, some were and some weren't. Remember that one that had a y to the 1/2? No, that wasn't linear. So here we're going to deal with linear equations. Now, time out a moment here. In differential equations, and someone has told me a little acronym, acrostic, whatever you call those things, that they heard, and I can't remember what it is now. It starts with S. I know the L's in there, the E's in there. All the things we're going to talk about here are there, and it spells something. I was going to say slime, but I don't think that's it. It's some sort of thing like this. If you can solve an equation by separation of variables, please do so. That's the easiest way to go. But there's some linear equations you cannot solve by separation of variables. So then we have to have another technique to do for this. So if we're looking for solutions for first order differential equations, and you have some that can't be solved by separation of variables, check next to see if it's a linear differential equation. If it is, we're going to hit a technique that works for that. So here's your definition of that linear equation. Okay, and this is in the most generic form. First order differential equation of this form: some coefficient function a1 of x dy dx, first order differential equation, plus some other coefficient function a0 of x times y is equal to some g of x, some arbitrary function of x. Okay, now remember, for this to be a linear equation in y, the dy's can only be to the first power, and your y's can only be to the first power. You can't have any cross multiplications or anything else like this, just that. It doesn't matter what these a functions or g functions are. They're functions of x. They don't have to be linear. They don't have to be anything. They just have to be functions of x. That's said to be a linear equation in the variable y. Now, at this point, you can probably see that there's a lot of these that can't be separated due by separation of variables. Okay? Now, this is your most generic form, but this isn't the one we want to use. What we're going to do now is divide everything on both sides of the equation by this a1 of x. Okay, now time out for a moment here. Let's see if they said this earlier. I don't recall seeing it, but let me just see. No, I don't see it here. Okay. This is not a differential equation if this a1 of x is ever equal to 0, is it? If that a1 of x is equal to 0, then this whole thing disappears, and you have a linear, not differential equation, just a linear equation in y. X may not be linear, but you have just some function of y. Well, that's pre-calculus algebra stuff. That's not differential equation stuff. So basically what I'm getting at, this a1 of x should not be equal to 0 for any value x in your domain. Okay? In the interval of integration, it should not be equal to 0. Because if it is, you no longer have a differential equation. So that makes it legal to divide everything by a1 of x, because it's not equal to 0. That's the only thing about dividing by a function. You got to make sure it's not equal to 0. This one should not be. So if you do that, then this becomes a0 of x over a1 of x, and this becomes g of x over a1 of x. Well, guess what? Those are still functions of x alone. So let's rename them, and rename that a0 of x divided by a1 of x to be p of x. Now, I don't like that name, okay? And I'll tell you why I don't like it, but that's what they always use, so I can't do anything about it, okay? The reason I don't like it, usually capital P stands for a polynomial function. We've just said this came about by dividing a1 of x by a0 of x by a1 of x. Now, if a1 of x is a constant and a0 of x is a polynomial, no problem. Or if a1 of x was a factor of a0 of x, no problem if that was a polynomial function. But this does not stand for polynomial function. So if you got that in your brain, sort of erase it for now. That was back in pre-calculus algebra. That's what p of x stood for. And then this other one, g of x divided by that, that's just some f of x. Nothing, no problem there. All right. So this is what we call our standard form for a linear differential equation. If you don't have it in this form, get it in that form. Step one. Okay. Now, what happens next is a long involved set of blah, blah, blahs of how they're going to go about solving this. Okay? Well, before we do, before we examine a general procedure for solving that, let's note some instances that can be solved by separation of variables. This one can. See, that's a dy dx plus 2xy is equal to 0. All you have to do is move the 2xy over here, multiply, or write it in differential form, divide by y. Separation of variables, do it. Don't go through the process of what we're going to do later. This one, however, no way. You can't do that. Well, no, I'm sorry, you can't. Because y plus 5 has no x in it, write that in differential form, and then divide by y plus 5. Yeah, no problem. Do separation of variables if you can do it. As both are linear equations, they follow this form right here, but they're much easier to do by separation of variables. But this one, on the other hand, is a linear equation, but it's not separable. Because if you multiply, well, there's just nothing you can do, because this y is related to that x in a sum or a difference form, not in a product form. So that's not separable. It looks awfully easy, but it's not separable. So this is one that we'll be using the form we're going to do. So here comes the method of solution. And if they can find a way to muddy the waters, you really need to go through all this mess. Okay, so here's the method of solution. Method of solution for solving a linear function that you can't separate. It works if you can, but why go through it? It hinges on a remarkable fact that the left-hand side of an equation, let me go back and show you what equation they're talking about. This one right here. The left-hand side can be recast, is the term they use for it, into the form of an exact derivative of a product by multiplying both sides of an equation by a very special function, mu of x. Okay? So, that's pretty nebulous, isn't it? They haven't told you what mu of x is. That's what the rest of this analysis is going to be, trying to figure out what function, mu of x, will make this magical thing happen. Okay? So, what we're going to do to begin with, let me scoot this up some, is going to be multiplying everything on both sides of the equation by that mu of x. Okay, now obviously mu of x should not be 0, because then you wiped out all meaning. So as long as mu of x is not 0, it's a legal thing to do. So multiply this by mu of x. It says it's relatively easy to find the mu of x because we want, let me go back and rephrase what my recast was. Okay, go back to this equation here. Okay, what we want this left-hand side to be is a perfect derivative of mu of x times y. Okay? Now, we want it to be an exact derivative of mu of x times y. That's what we want it to be. Okay? This left-hand side to be something like this. Okay? Now, that's what we want it to be, so let's see what it's going to take to make that happen. So since we want it to be some function of mu of x times y, if you take that perfect derivative of it, and this is merely the product rule, that's mu times dy dx plus y times d mu dx, right? Product rule. Okay. Now, that's what we want it to be. Now, if we go back up here, sorry, I keep The screen's not, oh goodness, I can't do that. I forgot. This is such a big file. How far off did I get? Pretty far, but not too bad. Okay. I have to use my, okay. Remember, this we want to wind up being a product of y times some other function that turns out being a perfect derivative. Okay? That product function to be a perfect derivative. Okay? So we want this to be that. Well, let's see what we've got here. We've got mu times dy dx plus mu times y. Well, okay. This right here was what we get from the product rule. Well, this first term is multiplied by mu, right? This next term is a y in there, and you've got a d mu dx. Now, what we want that to be, strangely enough, is that d mu dx to be exactly mu times p. Because you see, if you multiply both sides of this equation by mu, mu here and mu there, this is what you would get. If you take the derivative of this, this is what you would get. So this is that, so those are okay. What we want to happen is the d mu dx to be mu times p. That's what we want to happen. All right, that's our goal. Now this all seems pretty nebulous, but that's what we're going for. Oops. What did I just do? I'm sorry. It just went back to where it was before. I think I know why it did. I hadn't moved my cursor down. So let me try to, sorry about this. Let me get my cursor down here so I don't do that again. Okay. All right. Somewhere I hope it's here. We want this thing here, d mu dx, to be mu times p. Okay? Now, what we do there is separate these variables. Well, yeah, separate these variables. Remember, p is a function of x alone. So write this in differential form. d mu is equal to mu times p of x dx, divide by mu, and guess what we get? Mu of x is equal to p dx. Okay? d mu over mu is equal to that. If you integrate both sides of this, this gives you log mu, and remember mu is a function of x. You need the absolute value bars there because you can't take log of a negative number, so make sure that's absolute value. And this just becomes the integral of p of x dx, plus some constant, okay? Now, time out. We don't know what p is. P is generic at this time, so that's why we're leaving it. That doesn't mean it's a non-elementary function. It means we just don't know what it is. Okay. Now, the next step is take the e of both sides, because e of a log is just going to give you your mu. So, and e of this thing is going to give you, this would be e to that integral, and this would be e to the c. Well, e to the c is just a constant. So let's move that and make it a different c and just multiply. So your mu of x becomes some constant c2 e to the derivative of the integral of p of x dx. Okay? Now it says there are infinite choices for mu, all constant multiples of this one, because it's multiplied by that, and all produce the same desired results. Hence, we simplify life, okay, if life was ever simple, by just choosing C2 is equal to 1. Now, that doesn't seem fair, but it works. So don't argue with it, just do it. So this gives you what that function mu is. It's e to the integral of p of x dx. We already knew what p of x was. We just don't know it's a generic form. But if that is an integrable function, integrate it and then e it, take it as an argument of e, that becomes your mu. That becomes your mu of x. That's called the integrating factor. Why do we call it integrating factor? You multiply everything on both sides of the equation by that mu, and it works. Okay? So, back up. We've been dealing with each individual tree as we got there. Let's back up and take a look at the whole forest. What have we done so far? Multiply both sides of the equation 2 by 3, this mu of x. Okay. Actually, you start by identifying your p, integrate the p, and whatever that comes out being, and this integration that you do here, that integration you do here with the thing, okay, this integration here, you never put a plus c with it. Not necessary. Just do the antiderivative of it without a plus c. Whatever that turns out being, take the e of that. Okay? That then is your mu. So multiply both sides of your original equation by this mu. Every term on both sides by the mu. Okay? Now, what we have then, this is your mu. Mu of x dy dx plus p of x times the e to the integral of p of x, y, is equal to e to the integral of p of x dx f of x. Now this is really awkward to write it that way, but since you don't know what p is, we'll do it, okay? Now, if you'll notice here, this indeed is a perfect derivative. This up here is a perfect derivative of a product, okay? The product is this e to the thing times y. Well, let's take the derivative and see. Derivative of e to the thing times y would be e to the thing times dy dx. Sure enough, that's true. Plus y times the integral of that. Well, the integral of this thing would be e to that thing, because that's what an exponential does, times the derivative of your integral, which is p to x. So sure enough, that does work. And that's why it's called an integrating factor. It enables you to do that. Now, since this is a perfect derivative, you just take the derivative, integrate this with respect to x, and you integrate this with respect to x. Because look at this. This is only a function of x. This is only a function of x. So you can integrate both sides with respect to x. And as long as this is an integrable function and not a, what did we call them before, non-elementary function, you've got your answer. You've got your answer right there. Whoops. You may not realize it, but you got, when you integrate this thing, you get e times y here. And then once you integrate this thing, and here you do put in the plus c, then you divide both sides by this e to the that, which means you're multiplying by e to the minus that. Now remember, that thing that we've got here, it's just some function. You don't always carry it around as an integral, but it's just some function, just like it is here too. And it's that over here too. Please don't try to memorize this function. You do the process, okay? And when you're actually dealing with a function, it comes out much, much easier. So, quick review. Solving a linear first-order equation. Remember to put the linear equation in standard form. dy dx is equal to some function of x times y. No, dy dx plus some function of x times y is equal to some other function of x. Okay? Soon as you have in that form, identify that first function of x, that p of x. Integrate that p of x dx with no constant of integration, just integrate it. Okay? whatever function that turns out to be, raise that to the e power. Make that the power of e. Okay? Now, no constant needed. Okay. Now, once you get that thing, e raised to that thing, whatever that turns out to be, multiply everything on both sides of the equation by that. Okay? And then the left-hand side will automatically be the derivative of a product. Okay? The right-hand side is whatever it turns out to be. Okay? Usually it's solvable, but if it's not, you leave it as an integral. Okay? Now, once you got it to this stage, integrate this side, and you just have this product. Integrate this side and see whatever you get. Okay? Remember, you don't have an integral here anymore. You've already evaluated it. Okay? So it's not as bad as it looks. Okay? And then, once you finally do that, divide by whatever your coefficient of y is. All right. Now we're going to do one. This one could have been solved by separation of variables. We're not. We're going to do it by the new rule we just did. So let's go to the whiteboard and do that. Okay. Let me move Billy out of the way here. She's always in the way. Okay. And clear the screen. All right, to clear this, you need it any longer? All right. Get my finger ready. Example 1, bottom of page 56. Okay. dy dx. Now we'll come back and do it by separation of variables, and you'll see it is easier. But let's do it this way just to practice the technique. dy dx is supposed to be an x minus 3y is equal to 0. That equal to 0 guarantees you could have done it, not guarantees, but in this problem, that you could have done it by separation of variables. Let's not worry with that now, okay? It just keeps it simple for our first example. All right. First, it's in standard form. dy dx is by itself. This is just a function of x, a very simple function of x, constant function. This is an even simpler function of x. So you're in perfect shape. And this y is to the first power. That has to be a linear function. So identify your p. Do it right here. P of x, pretty easy. Is equal to minus 3. Identify that p of x. That was so easy. Then you integrate that p of x dx. I didn't leave enough room, sorry about that. And since that's a constant, that can go outside the integral and do just a dx here. P of x dx. You did a dx here, you do a dx there. Okay? Now, this thing here, we're not ever going to do it again. Let's integrate that. Well, that's going to be pretty simple. You tell me. How does that integrate? It's easy. Don't let it fool you. Negative 3x. Okay? And what's the next thing we do with that? Raise it as the power of e. So there is your integrating factor, e to the minus 3x. You found your integrating factor. Now you go back and multiply it by everything on both sides of the equation. So that gives you an e to the minus 3x dy dx
What is the number or letter when it says P to the X, and it's raised.
That's a dx. I didn't leave enough room. To do an integral, you need a dx. So I did a dx here, a dx there, and then integrated. Okay? Sorry. It's ugly. But yeah, that was supposed to be a dx. Is that what you meant? That thing right there?
Yes.
Yeah, that's a dx. Okay. So, multiplying this integrating factor by everything on both sides, the first side would be e to the minus 3x dy dx. Then you have a minus e to the minus 3x. Y, why not, is equal to, and guess what, e to the minus 3x times 0 is still 0. Okay, that side's easy. I'll do that all day long. Okay, now the thing to notice here. They claim this is a perfect derivative of the integrating factor e to the minus 3x times your y. That's what their claim is. It's a perfect derivative of that, and that thing is equal to 0. Okay? Let's see if that's indeed true. Let's take a derivative of this, and you get e to the minus 3x dy dx, perfect. I think I've done something stupid here, but I can't see where it is. Well, let's go on. That needs a 3 in it. Oh, yes, of course it does. This had a minus 3 in it. I put the minus sign, but I didn't put the 3. Sorry about that. And I multiply e to the minus 3x times that minus 3y. I just left off the 3. Whew. Okay, because the second part of your product rule would be, it's the first times the root of the second, that's what you got here, plus the second, y, there's the y, times the root of the first, and the derivative of the first would be e to the minus 3x times a minus 3, and there it is. Sure enough, that is the perfect derivative of this product. Okay? Now, what I like to do, and the book doesn't always do this, but what I like to do is now write this in differential form. On this side, it's the d of this thing, e to the minus 3x Ooh, that's ugly. Okay. Y is equal to 0 dx. Now that seems stupid to write, but I'm going to do it anyway. Later problems, you'll actually have something there, so I'm just going to do it this way. Now you integrate both sides. Okay? Okay. Oh, this looks stupid. This, the integral of a perfect derivative, is that integrand. E, or it's not an integrand there, it's the other thing. What you're taking the derivative of, e to the minus x, y. And what you have here, what's the integral of 0 dx? Antiderivative of 0.
Would it be a constant?
A constant, absolutely. C, whatever constant you want to call it. And then what you do is multiply both sides of the equation by e to the 3x to get alpha this side over here. So then your y is equal to c e to the 3x. There's your solution. First order linear differential equation, 1 constant of integration. Now, did they give us initial condition? No, they didn't. So that's our answer. Okay? Let's try it the other way. Okay? The other way was separation of variables. So much easier. Okay? That's why you always do it if you can. Let's first write this as dy dx. This is an ugly D. Yuck. Let me start that one over. The other one I didn't because I didn't have room. But boy, that's terrible. Okay. dy dx is equal to 3y, right? Adding 3y to both sides. Trying to separate the variables. So write it in differential form, and you have dy is equal to 3y. It's supposed to be a 3. It's supposed to be a y dx. Okay? Now, divide both sides by y. Okay? These go out. Now integrate both sides. And I'll keep the tree outside the integral. You don't need it inside. What's the antiderivative of dy over y? Help me, somebody. Natural log of y.
Log of y.
And technically you should put it in absolute value bars. Is equal to, what's the antiderivative of dx?
Constant?
No, not constant.
Oh, wait, a dx.
X, okay? Yeah. And you got to 3 times it, so that will be 3x. Okay. Plus some constant c. I probably should put a subscript on it, but I'll just call it c for now. Well, how do you undo a log? You e it, right? If you e that side, e this side, e of a log, e of log y would be y, and e of log x. In fact, let me do this, write this constant not as c, but as log c. Okay? And then you're doing e of a sum, which is the product of the exponentials. So that would be e to the 3x. For some reason, my x's wind up looking more like k's, but I can't help it. Times e to the log c, which is just a constant. I just chose to name it that. And e to the log c is just simply c. So that would give you c. That's supposed to be a c e to the 3x, which is exactly what we got using the linear. That's an ugly x, and this is an even uglier c. Same answer, okay? So sure enough, that's right. And you can check it by taking the derivative. dy dx is equal to 3c e to the 3x, right? And minus 3 times c e to the 3x, that gives you 0. Yeah, both of those are correct answers. And you've got it. You've done your first linear, solved your first linear differential equation. Y is equal to e to the c e to the 3x. And that's good for all values of x's, from plus infinity to minus infinity. Remember, what we were concerned with was your y. It had to always be positive, right? Because you're taking the log of y. But you see, e function is always positive, so as long as that c is positive, you're in no problem at all. So all you know is that c always has to be positive, because e to the 3x is always positive. Okay? Now, any questions on that? So let's go back to our Bookshare, and We got about 30 minutes to go, and frankly, I don't think my bladder's going to make it, so do you mind taking a quick break? Now, the bad news here, folks, is I thought I started Screencast-O-Matic again. I must not have. Let's see if it's running somewhere in the background.
Hey, Dr. Fowler, I have a question.
What's that?
I have a question.
Yes, what is it?
When we turn in our test 1, you just want us to scan it and send it back in through the messages, or?
Okay, good question. Let me go over. I may have mentioned this before, but in case I have, I'll go over it again. Okay, you have several options. Okay, if you have some way to scan it, and then once you've scanned it, get it in PDF format. You can attach it to an email and send it to me that way, or you can do an attachment on a message, Blackboard message. Either way. Or if you don't have the capability of scanning at home there, you can take a picture with your smartphone, and usually that's going to be in a JPEG file or something like that, and then you can either attach that to an email or attach it to your message on Blackboard. Okay? And I actually last term had a student who preferred mailing it, and I don't know why, but she did. It'll just get here later, but you can do that as well. Yeah, good question. Did that answer it?
Yes, sir.
Okay, good deal. Now, what I was just saying is I was trying to figure out what in the world happened to Screencast-O-Matic. I can't see it. So I don't know if it's recording. Sorry about that, folks, if it's not. But anyway, whatever it's doing, I've got to run to the restroom. I'll be right back. Hang on. I'll be back. Take a little break. Get up, stretch, whatever. Y'all get to do that all the time. I don't. All right, I'm back. Thank you for allowing me a break. That's just water, by the way, folks. Okay, so let's go back to the book. I don't know where Screencast-O-Matic wound up, what it wound up doing today. It says it's there, but I can't see it. Okay, so let's go back to the book. All right. Let me move Cole out of the way. Cole's always in the way here. Okay. Now, there's our answer. Y is equal to e to the 3, c e to the 3x. And there's them going through the things in the book. They may have skipped a few steps, but it was not too bad. Okay. Let's go to the next one. This one also could be solved separation of variables, okay? But we're going to solve it by linear technique, okay? And then we'll go back and do a quick check and see if it works the same with separation of variables, which it will. So here's the function, the problem, dy dx minus 3y is equal to 6. All right, so sorry about this. Go right back to the whiteboard. Okay, and now get these people out of the way. Okay, and clear the whiteboard. Anyone need that any longer? Okay. Now, example 2 was dy dx. I don't know why they have a window there. Can y'all see the whiteboard? Let me write something on it and then ask you that question. Dy dx is equal to, no, minus 3y, sorry about that. Minus 3y is equal to 6. Now that looks an awful lot like the last problem, doesn't it? Only difference is we've got a 6 there rather than a 0. Now my question to you is, can you see that, or has this big old rectangle suddenly got in the way?
I can see it. You
can see it. That's amazing, because it says move this window from the shared application, and yet, okay, all right. All right, so let's move on. What's our first step? Make sure you're in standard form. Coefficient of the dy dx can only be a 1. It is. So once you're guaranteed you're in standard form, then identify what your p of x is. And that is your minus 3 again, just like we had before. So do you need to go through all that, or can we jump right to where we left off before? I wish I'd have left that on the screen now. The p of x is equal to minus 3. I learned a little something, didn't I? To leave more room, okay. Minus 3, okay. So what do we do with that p of x? We integrate it, dx. Ooh, that's an ugly d. Still can't figure out what it is, can you? You integrate this, dx. Same thing we did with the p, only thing is there was something inside that one there isn't inside this one. And when you integrate that, you find it's equal to minus 3x. Don't ever put a constant with this, just minus 3x. Same as before. And what do we do with that? We e it, okay? We do the e of it. That becomes our integrating factor, the mu. Now we multiply that by both sides of the equation. E to the 3. I don't know how that happened. I'm saying one thing and writing something else. Okay. All right, let's get it. Whew. All right. Multiply this by everything on both sides. That's an e to the minus 3x dy dx the bottom d never turns out as well as the top one, it seems like, minus 3y e to the minus 3x. But this time, not nearly as easy as it was before, now we have is equal to 6 times e to the minus 3x. Okay. Multiply everything on both sides. Before it was a 0 there, that was easy. Now it's 6 times e to the minus 3x. Now supposedly this right side should wind up being a perfect derivative, not that perfect, okay? D by dx of the product of your integrating factor e to the minus 3x times your function y. That's what it should be. I always verify it to make sure I haven't done some stupid mistake like I did last time, okay? That's why I verify it. And this side just becomes 6. I don't know why it's writing even though I didn't press down on it, but we'll manage 6e to the minus 3x. Okay. Let's verify and see if that is a perfect derivative. Derivative of a product is the first times the root of the second, e to the minus 3x times dy dx. Perfect. That term is absolutely right. Plus the second, y, there it is, times the root of the first. And the root of the first is e to the minus 3x times the minus 3. There's your minus 3, and there's your e to the minus 3x. Sure enough, that is a perfect derivative. So what we do now, what I like to do is write that in differential form. This will be d of e to the minus 3x times y. Probably should have written the y first, but I got started on that. And then make this, move my dx over here, 6 e to the minus 3x dx. Okay, then we're going to integrate both sides. I'll put the 6 outside the integral because I don't need it inside, or maybe don't need all of it anyway. So anyway, the integral of a perfect derivative is the argument, which is e to the minus 3x, it's supposed to be an x, okay, times y, and this is equal to, on this side we can integrate, can't we? The 6 is on the outside. How good is your integration? What's the antiderivative of e to the minus 3x? Anyone want to make a stab?
Is it e to the negative 3x divided by 3?
By negative 3.
Oh, by negative 3.
Yeah. Okay, absolutely correct. Okay, and that negative 3 will divide into 6 a negative 2 times. So I'm going to put the negative 2 here. It's ugly, I'm sure, but okay, my writing is ugly. Okay, you also need a constant of integration here, and this time I think I'll make that constant of integration, even though my pen is doing whatever it wants to here. Okay, it quit. Okay. I think I'll just leave it C this time. Let's just see. I may change it later. Okay, then what we're going to do is multiply both sides of the equation by e to the 3x to isolate the y and get it just as a function of y alone. So that'll be y is equal to, okay, the minus 2 is still there. Okay, now when you multiply this by e to the 3x, just like here, it disappeared. Okay, so you're just left with a minus 2 plus c e to the 3x. Minus 3, no, e to the 3x, because you're multiplying by that. E to the 3x. Okay, that I think is your one parameter solution to this first order differential equation. Now, let's just do a quick check and see. If you take the derivative of this thing, that goes to 0, and this gives you 3c e to the 3x minus 3 times a minus 2, that's a plus 6, minus 3 c e to the 3x plus c I can't do it in my head too well. Let's take the derivative. I'm just going to call this y prime. I know they like calling dy dx. I'm just going to call it this. This is equal to 3 c e to the 3x. Okay. Now I'm going to add to that, or subtract from that, a minus 3 times y. So that's a minus 2 is a plus 6. Minus 3 times a minus 2 is a plus 6. And then you're going to have a minus 3 times c e to the 3x is a minus 3 c e to the 3x. And then you have that thing should equal 6. And guess what? This and this adds to 0, and that 6 equals 6. Yes, it does. Now, do you want me to see it? Do you want to see me do it by separation of variables, or do you think you can handle that yourself? I'll be glad to do it. It's not that hard. Want to see it just for a review?
Just for review.
You do? Okay, let's do it. So, up here, we'll write the dy dx. I'm going to skip a step here in just a minute. Is equal to 3y plus 6. Agreed? I just added 3y to both sides.
Oh, okay, then yes.
Just not to have to write it again, okay? I just added 3y to both sides, okay? Now write it in differential form, and that would be dy on this side is equal to, and I would write 3y plus 6 dx. I'm just going to write the dx. Is that okay? Because what I want to do next is divide both sides by 3y plus 6. So I'm going to bring that over here. Was that skipping too many steps?
No.
Okay. Now let's integrate both sides. Now, actually, I'm going to factor out a 3 in that denominator and make it a 1/3 on the outside of that integral. And then that would have been the integral of dy over y plus 2. Okay? If I factored out the 3, that would have been dy over y plus 2, right? And the antiderivative of that is the log. Natural log of technically absolute value y plus 2. Because I factored out that 1/3. And that should be an absolute value bar there. It didn't look like one. Okay? And that's equal to x plus c. But I'm going to make that a plus log c, if that's okay with you. Still a constant, right?
Why does did you put a log? Did you put the natural log that way they matched on both sides?
Okay, say that one more time.
Did you put the natural log so that way each side had one?
Yes, that is exactly it. Because I'm going to E both sides, and it's going to be easier to E in natural log than E in a constant, and then you have to change the constant. Yeah, that's it. You caught me. I was just being plumb lazy. Okay? Or you could say it's foresightful, but whichever you want to call it. Okay? Now, what I'm going to do is multiply both sides by 3. In fact, I'm not quite as foresightful as I thought I was, because this would just give me a log of, well, to keep the absolute value, y plus 2. And that's equal to, now I wish I would have done it slightly differently, but it's still okay, 3x, because I'm multiplying both sides of 3, plus 3 times the log of c, which is really the same as log of c cubed, right? But then let's just say that's log of c, okay? I just don't like to write lots of exponents. It's a different c from the first one, but it's still a constant, okay? Now, different c from the one above. That c is c cubed from above, okay? Now I'm going to E both sides, okay? That's the silly way to say it. If you E this one and E this one, this gives you y plus 2. You could still put the absolute value on it, but you'll see in a minute, once you E both sides, E is never negative, so you don't need the absolute value on it. So this now gives you a product. The log of a sum, the exponential of a sum is the product of their exponentials. That's e to the, that's an x. How in the world did that become a 3? Y'all let me get away with that? What are y'all thinking? Okay? I don't know how that happened. How did that become a 3? I have no clue. Oh, it's a 3x. That's what it was supposed to be. Now I see. Yeah, that was a 3x. Okay. I just forgot my x part. 3x. That was what it was. Plus log c, which is c is now c cubed or whatever. Okay. And then this would be e to the 3x. Down here. This is e to the 3x. And this is times e to the log c, which is just going to be c, and then subtract 2 from both sides. So y is equal to c e to the 3x plus minus 2. Okay, and what do we get before? Y is equal to c e to the 3x minus 2. Well, I wrote the minus 2 in front before, wrote it after here. Same answer both ways.
I had that on the other side, it was c e to the negative 3x. Should it not be?
Right over here?
Yes.
On this one. Okay. What I was trying to do was isolate the y here. And how do I isolate the y if it's multiplied? Now let's think about what e to the minus 3x is. That's 1 over e to the 3x, right?
Yeah.
And how you get rid of a 1 over e to the 3x is multiply everything on both sides by e to the 3x. So no, that becomes, are you saying this statement here?
I have, so
Yeah.
I understand.
Yeah. Go ahead.
Helpful. I understand how you got it here. I understand how you got it here. But I had it that my answer is y equals minus 2
Right.
plus c.
Okay.
3x.
No, okay. How you got rid of this one, e to the minus 3x, and that e to the minus 3x was multiplying everything on both sides by e to the 3x. That made that go to 1, that made that go to 1, but then you multiply the c by e to the 3x, not minus 3x.
Got it. Okay. I must have just written it down wrong.
Right. Yeah, that is a plus. Yeah. Good question, though. Any other questions? All right. So that was example 2 on page 57. Okay? Now, I'm not about to draw the graph, so let me get out of this. If I can ever get my cursor. Oh, there it is. Well, there, somewhere here. Let's go back to the text. Unless there were questions there, I can go back to it if you want me to. Let's get Melissa out of the way again. She's always in the way. Okay, here we go. All right, so there is our answer. Y is equal to minus 2 plus c e to the 3x. And that's good for all values of x, because exponentials defined everywhere. And you don't need the absolute values anymore because this thing is indeed always positive as long as c is positive. Okay? Now,
we have 5 minutes left, FYI.
Say that one more time.
We have 5 minutes left.
Yes, okay. And I think we can wrap this up in less than that, but let's just see. I'm trying to see where they got the A's here. When A1, A0, and okay. That's way back in the very first example there. When A1, that was the coefficient of your derivative, A0 was the coefficient of your y, and G was your function on the right-hand side of the equal sign. If those are all constants, then the differential equation is autonomous. Yes, okay? There was no, just like we saw here, this was autonomous differential equation. Remember when we talked about those, we would have then said that if you had added 3y to both sides like we did, and it said dy dx is equal to 3y plus 6, factor out the 2, and that would have been, factor out the 3 times y plus 2, that would have given y minus 2 to be your critical value, okay? Y equal negative 2 would have been your critical value, and then we would have seen what these functions were doing from there, okay? Now, and that it's unstable, a repeller, and that it's going away from it in both directions here. Thus, the solution with an initial point either above or below the graph of the equilibrium position solution y is equal to negative 2 pushes away from the horizontal line as x increases. And this is with the attainment of a graphing utility shows that y equal to with some additional solution curves. I don't say what those curves are. That sort of irritates me. What the values are here. I guess those are various C's that you have in there. but we've already said, or I think I pretty much said, that the C can't be negative. So I'm wondering if any of these really make sense. I don't know. I don't think that's worth time pondering, especially since we have 2 minutes left. So let's go on down and see what the general solution says here. Suppose again that the functions p and f in your linear form, standard linear form, are continuous with on a common interval I. Then all the steps that led to our final solution, we showed that if that initial thing, that standard form 2, has a solution on I, that it must be of the form given in 4, which we've already passed that a long time now. This is a lot of blah, blah, blah here. In other words, 4 is a one-parameter family of equations, and every solution of 2 is defined on that interval. Defined on the interval is that. Okay. Remember, we called that equation 4 the general solution of a differential equation on some interval I. That's just going back over plowed ground. Okay. So let's see if there's anything. So I guess all they're saying is then you can add your initial value to it and figure out what the specific number is. I don't know why they're making a big deal about it now. We've been doing that. Okay. All right. I think we'll start next time with example 3, the top of page 58. Okay. Now, homework exercises in this section will include, okay, I've got an extra mark on the page I need to get rid of so I don't get confused next week. Okay, I think you can start and do any of the odds 1 through, goodness gracious, 23. Any of those are in the back of the book. I believe you can probably do. Okay? And we'll do the initial value problem next time. All right. Any questions?
It cut out. You said any odd up to what?
23. Up to and including 23. Yeah, I turned my head and was looking at the book. Okay. Let me do it on the, since I have the book here, I forget I have it. Oops, I can't use that one. Let's just scream down here for a ways. It'll get there in a minute. Okay, here we come, right here. Any of those odds 1 through 23. Okay, does that make it clearer? Any of them, the answers are in the back of the book. Good deal. Any other questions? All right, we went a minute over, but guess what? There will be no extra charge. Okay. One other assignment. Have a good, safe weekend. Okay? Any other questions? Perfect attendance. Keep it up, folks. All right, I'm going to stop the sharing. Don't like to share. And we're going to end the recording. And we'll end it for everybody. See if I can find my screencast-o-matic. It may not have recorded today.